Okay, so welcome to section 1.4. So 1.4 is fundamental identities. So fundamental identities. Okay, so let's recall the Pythagorean theorem for a triangle with a vertex at the origin. So that would be x squared plus y squared. And we had on the, when we were there, we used r, so r squared. Okay. For our hypotenuse, we use radius. So let's consider now. Consider that equation once again. So let me just copy and paste. We have x squared plus y squared is equal to r squared. What I'd like to do now with this equation is take each of the terms and divide them through by r squared. So I'm going to take each term and divide it by r squared. So whatever I do to one side of an equation, I do to the other. But notice, what do I get when I do that? So x squared over r squared, I can really think of it as x over r, quantity squared. Similarly, y squared over r squared, you could think of as y over r, quantity squared. And r squared over r squared, well, anything divided by itself is just 1. That's a terrible one. 1 should be straight up and down. 1. Okay. So, and recall, x over r was cosine. So this can be thought of as cosine of theta, but we square it. And in order to square a trigonometric function, we put the square before the theta. So we read this aloud, cosine squared of theta plus y over r is sine of theta. So this is going to be the sine of theta, and we're going to square that. Read aloud, sine squared of theta is equal to 1. And let me make sure we know why. And that's because we have that cosine of theta is always the x-coordinate over the radius. And we have that sine of theta is always the y-coordinate over the radius. So that's where we're getting that from. Okay. Okay, so now we can finally introduce the main Pythagorean identities. So the main Pythagorean, and these are very important. They are actually the whole course. The main Pythagorean identities. Okay, so let me actually do singular for the time being. Well, yeah, identity. Let me just do the first one for the time being. Notice I'm recording this near midnight. I should not be doing that. Okay, so the main Pythagorean identity is the one we gave above. Namely, it's cosine squared theta, cosine squared of theta, plus sine squared of theta. Try and color code it. Sine squared of theta is equal to 1. So this is the main Pythagorean identity. This is the most important one in this whole course. So I'm going to put a box around it so we know to remember this one. If nothing else, we need to remember this. cosine squared theta plus sine squared theta is equal to 1. It's very important. Okay, so, yeah, actually, let's consider. I'm going to consider now instead of later. Let's consider, because I did write identities, plural. And why did I do that? So let's consider that the main Pythagorean identity. Cosine squared theta plus sine squared theta is equal to 1. Copy, paste. What I'm going to do now is divide. Let's do divide by cosine squared theta first. So I'm going to divide each term by cosine squared theta. Divide each term, whatever I do to one side of an equation, I do to the other. So I'm dividing every single term here by cosine squared theta. Okay, so cosine squared over cosine squared is just 1. Anything divided by himself is just 1. However, if we look at this sine over cosine squared, we can write it as sine of theta divided by cosine of theta, the whole quantity squared. What is sine over cosine? That's interesting. We'll have to think about that. What do I always write first? I always write sine first, and then I write cosine so that we can calculate something. And what is that something? So this as well can be written as 1 over cosine of theta, quantity squared. Okay, so what do we have? We've got 1 plus sine over cosine is actually tangent. So we can write this as tangent squared of theta is equal to 1 over cosine. So when I flip cosine upside down, I know that s's and c's go together. So whatever his reciprocal is begins with an s, so that must be secant. And since it's squared, it's secant squared of theta. So this is actually another Pythagorean identity, but we'll get to that in a moment. So actually, for the time being, let's go ahead and put a box around this. So this is, but notice, in order to get this Pythagorean identity, I only really need the main Pythagorean identity. So let's consider again, if I were to use this main Pythagorean identity, but instead of dividing through by cosine, let's divide through by sine and see what happens. So I'm going to divide everything by sine squared of theta. So dividing each term by sine squared of theta. Whatever I do to one side of an equation, I do to the other. So now what we're going to have over here on the left, let's see, should probably use, I'm going to have cosine of theta divided by sine of theta, and then I'm going to square that whole thing because each of them is squared. Plus, okay, well, sine over sine, or anything divided by himself, is just 1. So this will be equal to the quantity 1 over sine of theta all squared. Get that 1 in there. Okay, so cosine over sine, well, that looks like tangent upside down. So tangent upside down we know is cotangent squared of theta. Plus 1 is equal to, well, s's and c's go together. So since sine begins with an s, his reciprocal begins with a c, so it must be cosecant squared of theta. And this, of course, would be the third Pythagorean identity, once again derived from the main identity, so we don't really need to annotate it, but because I started, let's go ahead and list them now. So the Pythagorean identities. Pythagorean identities. So we always list the main Pythagorean identity. Cosine squared theta plus sine squared theta is equal to 1. Then I like to list as the next one the tangent one. So if I divide each of these terms by cosine squared, that'd be 1 plus sine over cosine is tangent squared theta, and 1 over cosine is secant squared theta. Or I could just look back here at what I got. And then the next one, what color shall I use? I have number 3. Be if I divide the main Pythagorean identity by sine. So that would give me cotangent squared theta plus 1 is equal to cosecant squared theta. So these are the 3 Pythagorean identities, of course the most important of which being the first one. So let's make sure we know this one very well. Cosine squared theta plus sine squared theta is equal to 1. This is very important. Okay, the other 2 are important as well, so maybe I'll just go ahead and put boxes around them. Let's know all of them, but really we can derive these 2 from the main one. So there we go. Each one has his own box, so he must be important. Okay, so let's recall. I used something when I did the derivations here. I used the identities, the reciprocal identities. Okay, so let's recall. Tangent of theta is sine of theta over cosine of theta. Then we had cosecant of theta. S's and C's go together is 1 over sine of theta. And secant of theta, S's and C's go together, is 1 over cosine of theta. Remember those? And of course cotangent of theta is 1 over tangent of theta. What's interesting, though, is if I wanted to, I could say, okay, well, sine of theta must be 1 over cosecant then. S's and C's go together. I can just take the reciprocal. So turn everything upside down. And I get that identity. Similarly, I could say that cosine of theta is 1 over secant of theta. So these are equivalent statements. That which is above it and that which is below. Right? As above, so below. Okay, so now let's do the fundamental trigonometric identities, some of which I just stated, so that's good. The fundamental trigonometric identities. Trigonometric identities. Okay, so what did I say? I said that sine of theta can be thought of as the reciprocal, or 1 over, cosecant of theta, CSC. Similarly, and cosecant of theta can be thought of as the reciprocal to sine, 1 over sine of theta. They are one another's reciprocals. So it goes both ways. Similarly, we have that cosine of theta can be thought of as a reciprocal to his function, his grouped function, which is secant, and vice versa. So, and secant of theta, of course, we know to be the reciprocal to cosine, 1 over cosine of theta. Okay, let's see, maybe a bit darker. What's the next one? The next one is tangent of theta. Well, this is sine over cosine, agreed? Sine of theta over cosine of theta. That's one way to look at it. And cotangent of theta would be cosine of theta over sine of theta. But there's another way to look at tangent and cotangent, and it is as follows. We could say that tangent of theta is 1 over cotangent of theta, and vice versa. Oh, I forgot to put the and last time. So let me put the and in there, and cotangent of theta can be thought of as 1 over, or the reciprocal, to tangent of theta. So these are the fundamental identities, the most basic trigonometric identities. Not to be confused with the Pythagorean identities, which are very important. So these Pythagorean identities are extremely important. Okay, and so I want to note something before we go on. So let's note. In the Pythagorean identities, we have the following groups or groupings of trigonometric functions. Trigonometric functions. So for the main Pythagorean identity, we have sine with cosine, namely cosine squared theta plus sine squared theta is equal to 1, so i.e. cosine squared theta plus sine squared theta is equal to 1, so we group sine and cosine together for that Pythagorean identity. The next would be tangent with secant. So that would be dividing by sine, dividing by cosine, the one above, that'd be 1 plus tangent squared theta is equal to secant squared theta. So that's the second Pythagorean identity. And the final Pythagorean identity is cotangent with cosecant. Cotangent with cosecant. So these are the groupings in the Pythagorean identities. So cotangent squared theta plus 1 is equal to cosecant squared theta. Okay, and that'll come into play. These groupings, it's good to know that the identities, sine with cosine, those are the two main x and y coordinates. Tangent with secant, okay, we just kind of have to accept that for now. But what's nice is cotangent goes with cosecant. So the cos go together and the tangents and secants go together. Okay, so don't worry, we'll come back to that. So for example, let's get back to our identities. So let's verify the following identities. So verify the following identities. Knowing identities. Okay, so in order to verify an identity, we always want to start on the ugly side. So let's say I gave you secant of theta times cotangent of theta is equal to cosecant of theta. So the ugly side, this is the ugly side. So we always start with the ugly side. So let's start with secant of theta times cotangent of theta. And we don't set it equal to the right-hand side. I'll show you why, because we have to verify, i.e. prove that this is true. So what is secant? Well, secant we know is 1 over cosine. So I'm going to use that. So I'm going to rewrite secant as 1 over cosine of theta. And I'm going to do the same for a cotangent, but I have two possibilities. I'm going to use the one that's cosine over sine. So I'm going to write this as cosine of theta over sine of theta. Because when I do that, I notice that cosine reduces. So what I'm left with then is simply 1 over sine of theta. So the purple 1 and the blue sine of theta. Okay, well, what is 1 over sine of theta? 1 over sine of theta is cosecant, so I can rewrite this as cosecant of theta. And is that the right-hand side? Yes, it is. The moment we get this guy here, we're done with our verification or proof. So our goal is to always simplify the ugly side to get the simplified side. Okay, so let's do another one. So number 2. Let's say we have cosine squared theta plus cosine squared theta times tangent squared theta is equal to 1. So what's the ugly side here? I claim the ugly side is the left-hand side. This is much uglier than the number 1, so this is my ugly side. So that's where I'm going to start, but I'm going to try and color code this. So I'm going to say, okay, so this is cosine squared theta plus, I'm going to keep cosine purple, cosine squared theta times, let's do blue, I guess, tangent squared theta. Now I'm not going to set it equal to 1 because I haven't verified this yet. So what I can do, however, is factor out the common cosine squared theta. So I'm going to factor out cosine squared theta. I'll have cosine squared theta on the outside. What I'm going to have then on the inside will be 1 plus tangent squared theta if I factor that out, right? Okay. Well, that's interesting. So I have cosine squared theta. And now I've got this parenthetical or bracketed remark. 1 plus tangent squared theta. Okay, well, let's go back to my, oh, look. 1 plus tangent squared theta is a Pythagorean identity. It's secant squared theta. So I can rewrite this as secant squared theta, and then I'll put an asterisk. And that's because 1 plus tangent squared theta is equal to secant squared theta, right? That's one of our Pythagorean identities. Okay, so now going back over here, I can write this as cosine squared theta. All whole numbers are over 1, so I'm going to put this over 1, and you'll see why in a moment. Because secant is what? Well, secant is 1 over cosine, so I can write this as 1 over cosine squared theta. Which is nice because now cosine squared theta and cosine squared theta reduces. So I'm left with 1 over 1 or 1. And that is exactly what we wanted because that is the right-hand side. So we have verified this identity. Okay. Number 3. Let's kick it up a notch, shall we? Okay, so let's say we have quantity tangent of theta plus secant of theta times the quantity tangent of theta minus secant of theta all over cosecant of theta, and that is equal to negative sine of theta. Okay, so it should be evident that the ugly side is here on the left. This is much uglier than negative sine. So ugly side. So I'm going to start with this ugly side. Okay, so let's go ahead and rewrite this. How shall I do this? What color should I use? I don't know what color to use. Okay. I'm going to use pink. And I'll have a plus and a minus. So let's use, for tangent, let's use purple. So tangent of theta. And for secant, let's use blue. Secant of theta. And for cosecant, let's go ahead and use green. Cosecant of theta. Okay, so it should be evident that what we have in the numerator is a difference of squares. I have tangent plus secant times tangent minus secant. So that gives me, when I distribute, first guy squared, tangent squared theta, minus second guy squared, secant squared theta. That is, this is the difference of squares. Okay, and that's all divided by cosecant theta. Okay, well, tangent and secant. I know that tangent and secant go together where? Well, they go together in the Pythagorean identity, right? I know that 1 plus tangent squared theta is secant squared theta. So let's go off to this side. Let's put an asterisk here. 1 plus tangent squared theta is secant squared theta. But that's not what I have there. I have tangent squared theta minus secant squared theta. Okay, so let's see. Let's go ahead and subtract secant squared theta. Subtract secant squared theta. So what I get then would be 1 plus tangent squared theta. Oh, that's a terrible tangent squared theta. Tangent squared theta minus secant squared theta is equal to 0. Okay, but I don't have the 1, so let's go ahead and subtract that out. Minus 1, minus 1. So now I have that tangent squared theta minus secant squared theta is negative 1. So I can replace that whole numerator here with negative 1. So I can just write this as negative 1 divided by cosecant. Well, what is cosecant? Cosecant is 1 over sine. Okay. So negative 1 divided by 1 over sine. Sine of theta. Okay. So I can invert and multiply. So this would be negative 1 times the reciprocal of the fraction in the denominator. So flip it upside down. This will now be positive sine of theta divided by 1. But of course, any whole number or anything divided by 1 is just itself. So we get negative sine of theta. And guess what? That's exactly what we were looking for. That is indeed the right-hand side, so check mark, we did it. We've established or verified the identity. Okay, so hopefully that makes sense. Let's do some more. So for example, so let's use identities. So use identities. Identities. To express the given trigonometric function. So to express the given trigonometric function. Given trigonometric, or let me just write trig. I think you get it at this point. Trig function. Although I'm not a big fan of contractions, so trig function with respect to, and now here I'm going to go ahead and use a math term. WRT means with respect to. That's on your symbol sheet. The indicated function. Indicated function. Okay, so number one. Let's express secant of theta with respect to, let's do tangent of theta. Secant and tangent. Okay, well, I know that secant and tangent, they're related by the Pythagorean identity. Namely, 1 plus tangent squared theta is equal to secant squared theta. So if I wanted to solve for secant squared theta, all I would need to do to 1 plus tangent squared theta, or to both sides actually, is to take the square root. But whenever you take a square root, you have to do plus or minus. So plus or minus. Okay, so taking the square root of something squared gives us, so this will be plus or minus the square root of 1 plus tangent squared theta is equal to just secant theta. Because the square root of something squared undoes the square. So there we are. So secant is plus or minus the square root of 1 plus tangent squared theta. Okay, so now let's do another one, number 2. So let's evaluate cosecant of theta. Now with respect to, let's do cosine of theta. Okay, well that's not so easy, but I am going to use a couple things. I'm going to use the reciprocal identity for cosecant. So I know that cosecant of theta is the reciprocal to what function? Since s's and c's go together, this must be 1 over sine of theta. Okay. So sine of theta, how is sine of theta related to, let me actually make this a different color so we can see it better. Let's use this color, sine of theta. So using my Pythagorean identity, I know that cosine squared theta plus sine squared theta is equal to 1. So subtracting cosine from both sides, minus cosine squared theta, minus cosine squared theta. I get that sine squared theta is equal to 1 minus cosine squared theta. So now I can take the square root of both sides. Let me rewrite this. So sine squared theta, I'll be taking the square root of that. Will now be equal to plus or minus the square root. So plus or minus the square root of 1 minus cosine squared theta. So I can replace this sine of theta right here with plus or minus the square root of 1 minus cosine squared theta. So So plus or minus the square root of 1 minus cosine squared theta. So now I've written cosecant of theta, which is still on the left-hand side of this equation, just with respect to cosine. So the only trigonometric function here is cosine. So that was kind of difficult. So let's see. Let's do number 3. Let's do tangent of theta with respect to sine of theta solely. Okay, well, tangent of theta, of course, is sine of theta over cosine of theta, right? So let's do color code this. Let's do sine of theta over cosine of theta. But once again, sine of theta in the numerator is fine. However, I don't want cosine. So let's go over here and redo the main Pythagorean identity again. So the main Pythagorean identity, cosine squared theta plus sine squared theta is equal to 1. So let's isolate for cosine. So now I'm going to subtract sine squared theta from both sides minus sine squared theta. So what we get then is cosine squared theta is equal to 1 minus sine squared theta, which means taking the square root of cosine squared theta, otherwise known as just cosine, will be plus or minus the square root of 1 minus sine squared theta. 1 minus sine squared theta. So actually, I should have probably written that thoroughly here. So this is simply sine of theta is equal to plus or minus square root there. Okay, and I'll do the same thing here. I'll just simply write cosine of theta. When you take the square root of something squared, you just get what's inside. Will be plus or minus the square root of 1 minus sine squared of theta. So that means I can replace the denominator over here. So I have that tangent of theta is equal to, in the numerator, we still have sine of theta in blue. But now in the denominator, I'll have this whole big plus or minus the square root of 1 minus sine squared theta. And what's nice about that, now tangent is written just with respect to sine. That's the only trigonometric function there. Okay. Hopefully this is making sense. Let's do evaluations now. So for example, let's evaluate the 6 trigonometric functions of theta in the following. So evaluate the 6 trigonometric functions. Trigonometric functions of theta in the following examples, or in the following period, following colon. Okay, so number 1. Let's say we have that secant of theta is negative 5 over 4. And theta is in quadrant 3. So that symbol means is an element of quadrant 3. That's on your symbols sheet. So let me make sure we know this. That this symbol, a C, means is an element or is in. Is in. Okay, so secant of theta. So secant of theta is 1 over cosine of theta. Okay, that's one way of thinking about it. But cosine of theta is x over r, so this must be r over x. Okay, so actually let me make r pink. So for us, we were given that secant is -5. Well, a radius can't be negative. So I know that that negative is going to have to go to the 4 in the denominator. So x is -4. And in quadrant 3, both x and y are negative, so that's good. Okay, I also know that x squared plus y squared is equal to r squared. So I can solve for y. So this will be quantity -4 squared. Actually, I don't need to skip a line. Well, maybe I do. I don't know. Should I skip a line? Okay, so quantity -4 squared plus y squared, which is what I'm looking for, is equal to 5 squared. Okay, so hopefully some of you recognize this as a 3, 4, 5 right triangle, but if not, let's go ahead and evaluate this. So we get that y squared is equal to, oops, wrong color, is equal to 5 squared is 25. Minus now, for a -4 squared is a negative times a negative, so it would be minus 16, because the negative is going to go away before we subtract it. So y squared will be, well, 9. So y is actually plus or minus 3. But since we're in quadrant 3, the y coordinate, so in quadrant 3 means that this implies, double right arrow, this implies y is -3. Okay. So now we can finally calculate the 6 trigonometric functions. Okay, so sine of theta, which we know is y over r, well, that's going to be what? -3 over, the radius can never be -5, right? Okay, so without having to think much, I know the reciprocal function cosecant of theta, because s's and c's go together, will be r over y. And that's going to be 5 over -3. Hopefully that makes sense so far. Okay, where was I? Let's go cosine. Cosine of theta is x over r. X we were given as -4, and r we were given as 5. So right away, the reciprocal function, secant, and if we've done everything right, it should be what we were given. Secant, of course, is r over x. So we should get -5/4, and that is exactly what we were given. Okay, good. Okay, so tangent of theta is just the quotient of the two above, namely y over x. So y over x is going to be -3 over -4, so that's just a positive 3 over 4. Two negatives make a positive. So therefore, the reciprocal function, cotangent of theta, will just be x over y, or positive 4 over 5. Okay, so x over y will be 4 over 5. Sorry, 4 over 3. What am I saying? Do as I say, not as I say. Do as I do, not as I say. I don't know at this point. Okay, so basically what's going on here? We want to see what's going on here. Here's our x and y coordinate axes. X and y. We know that x is negative 4. 1, 2, 3, 4. And we know that y is negative 3. So if we go to the point negative 4 comma negative 3, what we're saying is that this radius here is 5. The distance y, of course, is, as a distance, it's 3, but we know y is negative. So this is negative 3 down here. And as a distance, this is 4, but we know that this is the point negative 4. Actually, So that's what's going on here as far as theta being in quadrant 4. So what is theta? Theta measures from the positive x-axis all the way into quadrant 3, not 4. So there's my theta. Let me draw theta a bit better. Okay, so let's do another one. Hopefully you're understanding what I'm talking about, and you're not listening to this as late as I'm recording it. Okay, so let's say we have that cotangent of theta. Actually, let me move down a line. So cotangent of theta is negative 12 over 5. And let's say we want that theta is in quadrant 2. Okay, so maybe I'll go ahead and draw this first. So, oops. Oh no, what just happened? Okay, that was weird. Okay. So I'm in quadrant 2. Oh boy, 12 over 5. Okay, maybe I'm not going to draw it just yet. I'll wait on this, and then we'll come back to this picture. Okay, so cotangent, of course, we know that that's going to be cosine over sine, so cotangent is actually x over y. Okay, so in quadrant 2, I know that x is negative, so it is indeed negative 12. And I know that y is positive, so it's positive 5. So we're okay there. Okay, so what we get then, we're trying to find the radius. So we know that, did I actually state them here? Yeah, so we know that x squared plus y squared is radius squared. And for those of you who are savvy, this should be a 5, 12, 13 Pythagorean triple, but let's see. So this is going to be quantity negative 12 squared plus 5 squared is equal to r squared. Okay, so 12 squared is 144. 5 squared, of course, is 25. And that's equal to radius squared, or r squared. Okay, so this is 169 is radius squared. So it's actually positive 13 because radius is a distance, so I never have to worry about plus or minus with a radius because distances can never be negative. Okay, so my radius is 13. So basically what we have a negative x, so let's assume that this is 12 here. So negative 12 on the x. Then we're going up 5 on the y. Assume that this is 5 on the y in quadrant 2. Then our radius here will measure 13. So the angle theta that we're concerned with as measured from the positive x-axis is here. So that would be theta. Okay, so let's evaluate the 6 trigonometric functions of theta. So let's start with sine. So sine of theta is going to be y over r, and y we found to be 5, and we just figured the radius was 13. So the reciprocal to sine, given that s's and c's go together, oops, that's not letting me do that, that's not good, okay. So the reciprocal to sine will be cosecant of theta, which of course is going to be r over y, which will be 13 over 5. Okay, so now let's evaluate cosine of theta. So cosine of theta is x over r, and we found x to be negative 12, and we figured the radius to be 13. So the reciprocal to cosine, given s's and c's go together, is secant of theta. So that's going to be r over x, or 13 over negative 12. And finally, tangent of theta is just the quotient of the two above him, namely y over x. So y was 5 and x was negative 12. Therefore, the reciprocal function, cotangent of theta, which is x over y, is going to be negative 12 over 5. Okay, so hopefully this is making sense, and I will see you guys in the next video.